Second, can I introduce?
Yes, sir, please.
Yeah. Good evening, everyone. This is Sabrinath Babu from SAE India. I am the current acting DDG of SAE India. Let me introduce our speaker, Mr. Sharath. Mr. Sharath currently works as technology specialist at COMSOL Multiphysics. He received his master's degree in machine design from BMS College of Engineering in Bangalore. Before joining COMSOL, he worked on mechanical integrity assessments of Siemens gas turbines in TCS. Over to you, Sharath.
Yeah, thank you, sir, for the brief introduction. And so, good evening, everyone, and welcome to this webinar on modeling electric motors and drivetrains with COMSOL Multiphysics. COMSOL is a very versatile tool when it comes to modeling, multiple physics phenomena, and it is a general purpose tool. Right. So, in this webinar, we'll look at the different components of the electric drivetrain that can be modeled using COMSOL. Right. So, ranging from electric motors to the battery packs, and also the power electronic components as well. Right. Yeah, so within COMSOL Multiphysics, so it basically offers you one single software environment for any kinds of engineering field, right? So be it the structural mechanics, electromagnetics, CFD, heat transfer, or even several fields of chemical and electrochemical reactions as well. So all of this can be modeled and simulated within one single graphical user interface, right? So that can be for single physics or any sort of multiphysics phenomena as well, right? Such as the electromagnetic heating, so which plays a major role when it comes to the different aspects of electric drivetrains, right? So that can be modeled within one software environment. So before we start off with our actual presentation, so just to understand what kind of audience so we are having today, I request you to just kindly answer this particular poll question. Right? So I'll be launching this poll question. Yeah, so it should be visible on your screen as of now. So I request you to select the appropriate response. So maybe we'll wait for 10 more seconds until all the attendees have the chance to respond. Okay, so thanks everyone for responding to this particular poll question. Yeah, so meanwhile, please feel free to type in your questions in the questions tab. So maybe we can take up those questions at the end of the session, right? Yeah, so moving on with the presentation. So COMSOL offers dedicated features and material models when it comes to modeling your electrical machines, right? So these dedicated features are, where you can model your solid conductors. So it can be in the form of multi-turn coils or single-turn coils. So you can model your magnets in several patterns, right? So it can be linear patterns or circular patterns. You can model different kinds of electrical excitation in the form of multi-phase stator windings, right? So we have multiple loss calculation formulations when it comes to calculating the electromagnetic losses within your coils or the soft iron domains, right? So this can be several empirical formulations such as the Steinmetz formulation or the Bertozzi formulation, among others, right? So you can implement sector modeling into your particular electrical machine to essentially reduce the computational load on your system, right? So depending on the periodicity, you can decide upon the sector modeling. So there are several formulations to extract the torque output from your electrical machine, right? So we have formulations such as the RQO torque calculation feature, right? So when it comes to the magnetic materials, so there are multiple material models when it comes to the hard and soft magnetic materials. So there are features to implement magnetic saturations, and so typically in electrical machines, so we have various forms of iron and copper losses, right? So these can be hysteresis losses or eddy current losses, or they can be resistive losses, or what we typically refer to as Joule heating. Right? So all of these can be considered. So temperature dependency plays a very major role when it comes to the material properties, right? So especially the copper conductivity or the resistivity, right? So all of these temperature dependency can be considered into your material modeling while solving your electromagnetic modeling, right? So it is kind of parallel computation that happens between the electromagnetics and the heat transfer, right? Yeah. So any forms of your physical configuration of various machines can be modeled, right? So it can be a radial configuration or even the more modern axial flux machines as well. Right? So typically due to their inherent nature of higher power density and torque density, so axial flux configurations are preferred where larger power density is needed, right? So those configurations can also be modeled within COMSOL multiphysics, right? So if you have the CAD geometry and if it is physically feasible, it can be modeled in COMSOL, right? So yeah, similarly to the electrical machines that can be modeled, you can model various aspects of power electronics as well, right? So because in the recent times there is a demand for increased power density, right? So for that, so that automatically adds in several challenges for the engineers in the form of heat dissipation and thermal management, right? Because of COMSOL multiphysics inherent nature of multiphysics, so you can couple those effects, right? So the electromagnetic effect that causes the temperature rise can be coupled, right? So so we have several examples that we can probably discuss, right? Yeah, another important aspect of your electric drivetrain is the battery modeling, right? So we discussed on the electrical machine part and the power electronics part, but the major part of any sort of cell design or even at the electrode level design, so battery modeling plays a very vital role, right? So in COMSOL, the capabilities extend from the electrode level until the battery pack level, right? So you can start off with modeling your very heterogeneous battery electrodes, then you can homogenize the properties and do the analysis at the pack level as well. So if you're interested in the thermal management or thermal runaway kind of events, right? So that can be modeled. So in summary, you can start off with the cell models and integrate the cell level using the 1D models at pack levels, right? And you can do analysis such as the thermal management, right? So considering the various electrochemical heat sources, you can also do short circuit analysis as well. Right? Yeah. So in summary, the entire gamut of the electric drivetrain can be modeled within COMSOL. Right? Yeah. So just to understand what your main area of interest is, so we have another poll question. So this is mainly on what aspects of motors would you like to model? Right? So I'll be launching this poll question. So I request all the attendees to kindly answer this poll question as well. Right? So you should be able to see this particular poll question on your screen. So because within motors, there are multiple effects that can be modeled, right? So depending on the requirement of the customer. So we are just interested to know what is the aspect that is more in demand. Yeah, so maybe we'll take 20 more seconds so that all the attendees get a chance to answer, pick the appropriate responses. Right. So once again, thanks everyone. So for answering this particular poll question. Yeah. So let us move on. Right. So whenever we are starting off with designing a motor, so the first aspect is to model the various electromagnetic aspects of the motor. Right. And one of the major aspects of electromagnetic modeling is the loss calculation. Right. So these losses can be either due to several various hysteresis losses or also due to copper losses as well. Right. So which is basically the resistive heating. So as I was saying, so we have several formulations when it comes to these loss calculation features. Right? So this can be Steinmetz and Bertotti loss formulation. These are mostly empirical loss formulations. But let us say you have come up with your own sort of user-defined loss formulation, right? So even that can be easily, user-defined within the COMSOL graphical user interface, right? Yeah, so we have time to frequency loss formulations as well. So this is typically based on the Fourier transform that is implemented, right? Where we get the average cycle losses for the entire electrical cycle. Right? Yeah. So it is very important to consider the temperature dependency as well, right, on the material properties, because typically most of the material properties are dependent on the temperature, right? So that can be easily considered within COMSOL. For example, in this user interface that you see, within the multi-phase winding feature, so we are defining the coil wire conductivity. Right? So here you can see that the coil wire conductivity can be defined as a function of delta T, right? So which is the rise in temperature from the ambient temperature, and also the magnet BH curve is also a function of temperature, right? So this can also be very accurately, considered within your simulation model. Yeah, so once the electromagnetic modeling is done, the next step would be to extract the torque. So basically the electromagnetic forces that produce this particular torque at the interface of the rotor and the stator. Right? So for that, we have this arcuate torque calculation feature. Right? So with several predefined inbuilt variables that calculates the radial force density, azimuthal force density, and also the magnetic flux. Right? And so we have several tutorial models both in 2D as well as 3D. So maybe after the session, I request all the attendees to go to the COMSOL website and download these tutorial models. Yeah, so that can also be done. Maybe I can go to the website and show at the end of the presentation, if the time permits. Right? Yeah, so you can extend your electromagnetic analysis within COMSOL to include various structural aspects as well. Right? So since within COMSOL, you can also model the structural mechanics aspects of your motor model. Right? So you can extend the basic electromagnetic analysis, include several of the physics features, physics interfaces that are available under the structural mechanics, and do analysis such as the NVH analysis, right? So what we refer to as a noise, vibration, and harshness analysis. Right? So here you see the results of one such study. Right? The stress distribution in the housing is basically due to the various electromagnetic torque fluctuations. Right? So that can lead to stress distributions and stress concentrations within the housing and also in the rotor and the bearing assembly of the motor. Right? So all of these aspects can be very accurately investigated in COMSOL. Right? So here you can also see the rotor orbits for the two bearings, right? Because of the inherent vibrations, you can see how those orbits are basically distorted. Yeah, so based on the several concepts that we just looked at just now, so we have a case study from Volkswagen based out of Kassel in Germany. So Volkswagen has been a long-term user of COMSOL now, and they have been using COMSOL especially for motor modeling. Right. So here there is a multiphysics simulation considering the electromagnetics as well as the structural mechanics aspects, where they are actually trying to assess and evaluate the strength of the rotor laminations. So these laminations are very thin parts, right? So these are assembled. Several hundreds of these laminations are assembled within a rotor, right? And because of the various electromagnetic forces and because of temperature distribution within the rotor laminations, so this can lead to stresses and deformations within the laminations. Right? So here the researchers are basically trying to analyze what these stress distributions are and what are the maximum deformations that can be caused because of these electromagnetic forces. Right? So in the process, they've also developed an application. So within COMSOL, you can also develop applications out of your complex simulation models. Right? And you can share those applications with any of your, let us say, experimental group so that they can validate the results. Right? And in these applications, you only specify a set of inputs that the user can see, and changes in these inputs, how they're affecting your particular results. Basically, that can be investigated. Right? So this is one such case study from one of the major global players when it comes to automotive industry. Yeah. In the recent update that was released a couple of months back, so there was a new formulation that was announced, right? So which is the time periodic electromagnetics. So this is a game-changing approach in the sense. So in this approach, you're not doing time stepping while rotating the rotor, right? So you are basically considering time as a stationary dimension, right? So you are basically splitting up the time frames and solving for all of these time frames parallelly, right? So in a sense, it becomes a stationary kind of a study, right? So what advantage this kind of formulation provides us? You can do multiple parametric studies, right? So you can directly calculate the efficiency maps and temperature maps for your motors or any electrical machines, right? So since you're doing a stationary kind of a study, you can implement other physics as well, such as if you're interested in knowing the temperature rise or the temperature distribution, you can couple the electromagnetic model with the heat transfer. So if you're interested in knowing any vibrations or deformation, you can couple your electromagnetics with the structural mechanics physics interfaces, right? And if you're interested in knowing the noise output due to these vibrations, you can couple it with several of the acoustics interfaces as well. And optimization can also be implemented parallelly, right? So you can do any of the optimization techniques that are inbuilt within COMSOL. So this can be topology, shape, or parameter optimizations, right? Yeah. So this is one such game-changing approach in the sense. So it is a very efficient approach if you are trying to do any parametric or multiphysics analysis, right? Yeah. Maybe I'll also show one demo model as well, just to demonstrate what this is all about. So if we look at the results of such time periodic analysis, so this is one 2D analysis that has been done for the electric motor, right? So here you can see the plots of electromagnetic loss distribution and also the temperature fields at various operating points, right? So these operating points are different temperature, different speed values, and also the peak current values, right? You can see the various electromagnetic loss distribution and the resulting temperature rise distributions. And of course, within COMSOL, you can also extract the efficiency maps just to know what is the optimum speed range for which you can extract torque in a very efficient manner. Right. So that is what the efficiency map is all about. Right? Yeah. So extending the electromagnetic analysis. Like I was mentioning in one of the previous slides, you can also do structural mechanics analysis. In the sense, you can obtain the eigenfrequency values and the natural frequencies, and also the mode shapes for different natural frequencies. Right? So if you're interested in knowing any noise output because of the torque fluctuations, you can also do an acoustic analysis and obtain the sound pressure level in the surrounding air domain of the motor. Right? So here you can see the sound pressure level at different rotational speeds and also different harmonics as well. Right? So if you're interested in doing any dynamic analysis, so we can also plot what we refer to as the Campbell plots as well. Right? So here you're plotting the natural frequencies for different shaft rotational speeds. Right? So basically you do this to obtain different resonance frequencies. Right? Yeah. So in the sense, in COMSOL, you can perform a truly multiphysics analysis. Right? So starting from the very basic electromagnetics, you can include the various heat transfer and also the structural mechanics aspects as well. Yeah. So within time periodic analysis, so you can also implement different optimization strategies as well. Right? So yeah. So here in this example that you see, the objective of this optimization was to obtain a reduction in the torque fluctuations, right, by a factor of 2.5. Right. So these torque fluctuations are what causes the vibrations, right? So if we talk in reference to the automotive vertical, so the passenger comfort basically depends on the vibrations, right? So if there are large torque fluctuations within the electric motor that is there in your electric vehicle, so that can lead to loss in passenger comfort, right? So that is the reason to reduce the torque fluctuations, and in this case, that was the objective function of this particular optimization. Right? So while doing that, so we also had certain constraints that we had implemented. Right? So we wanted reduction in the iron material used, and also reduction in the maximum stress levels as well. right? So we were able to achieve both the objectives. Right? So here you can see that considering a multiphysics model, right? So you can obtain a uniform results, right? So here you can see the magnetic flux density distribution and also the von Mises stress distribution, right? By considering both the physics, both the electromagnetic and also the structural aspects, right? Yeah. So this is one such example. So discussing more on the motor optimization topic itself. So within COMSOL we have so we can implement optimization in several ways, right? So it can be parameter optimization, shape optimization, or topology optimization, right? And so in COMSOL the objective function can come from any of the multiphysics, any of the underlying physics, right? So within the electromagnetics, so your objective function can be a reduction in the torque ripple. So within the heat transfer, your objective can be, limiting on the temperature rise, right, to a certain extent. So within structural mechanics, it can be, von Mises stresses that you want to limit to a certain value, right? So there is a true support for multiphysics, right, within COMSOL. So here you can see one such topology optimization study that has been done for an axial flux motor, right? So where we are essentially removing the material out of the iron domain, right? Yeah, so when we talk about the parameter optimization case, so in this example, so this is an example of a 2D permanent magnet motor, right? So we go with the parameter optimization approach if we can parameterize any of the objectives, right? For example, here, the tooth width, the coil cross section, the back iron thickness, so the magnet width, height, and the magnet cross section. So all of these can be easily parameterized, right? So in this case, so we go with the parameter optimization approach. Here, the objective was to maximize the torque output from your motor, right? And the control variables were the tooth width, back iron thickness, and the magnet width and height. Right? So that can be basically changed or used as variables to obtain this particular objective, right? And we had a couple of constraints as well. The coil area conservation. So we did not want any reduction or change in the coil area, right? And also we wanted to reduce the magnet area by 10%. So that can lead to huge cost savings, right? Because the magnet is one of the more expensive materials within an electric motor. So these were the constraints. So if we look at the results of such an parameter optimization, so here you can see the initial design results, right? So that's what you see in the blue. So this is for the torque fluctuations. And if you compare that with the parameter optimized results, so you can see that there is slightly higher torque output, right? Which is the green curve. Yeah, so similarly, you can also do shape optimization as well, right? So in this case, so here the shape optimization, the objective was to reduce the torque fluctuation. So as I was saying, to enhance the passenger comfort, right? So here you can see the results of the shape optimized magnets, right? The red curve. You can see the torque fluctuation, the maximum and the minimum, the difference of the maximum and minimum torque. It has been minimized, right? So thus reducing the torque fluctuation. And here you can also see the animation of the shape optimization of the magnet itself. Right? So here it is continuously changing the outer boundary of the magnet. So thus the objective of reduction in the torque ripple is attained. Right? So yeah, so that is the example for the parameter and the shape optimization. Yeah. So maybe, yeah, so now we can switch over to a live demonstration, right? So we'll demonstrate the permanent magnet motor and how we can basically look at the efficiency maps, right? So we'll be using the time periodic interface, so which the game-changing interface that we were discussing about earlier, right? And we'll be coupling the electromagnetics interface with the heat transfer, right? So since we are plotting the efficiency map, and that is a function of the temperatures, right? So yeah, so right, so we'll be plotting the motor efficiency as a function of speed and torque, right? Yeah, so we'll see how that comes about. So I'll just quickly switch over, yeah, to the COMSOL interface itself. Okay. So for those who are new to COMSOL, So this is a general layout overview of the COMSOL graphical user interface. Right? So typically COMSOL interface can be divided into 4 major parts. Right? So one is the model builder. So model builder essentially has the different steps that you need to take to build your simulation model. Right? So this can be creating various definitions of parameters. So importing or creating geometry, CAD geometry. Right? So then assigning different materials into your geometry domains or boundaries. Right? And then different physics interfaces. So typically within geometry, so the different boundary conditions that we refer to as are grouped into physics interfaces, right? So that is how we assign the various boundary or the domain conditions. And then we also need to discretize our continuous geometry, right? So since COMSOL is a finite element based simulation software, so we need to create a mesh out of our continuous geometry, right? And ultimately, after that, we need to run our study. Then we have the post-processing, or what we refer to as the results and visualization. Right? Yeah, so this is on the model builder part. And we refer to each of these points as nodes, right? And for each of these nodes, we have a corresponding settings part, right? So whenever you click on the node, we have a corresponding settings part. So whatever options are available within the model builder, so same options can also be accessed through this ribbon on the top, right? So for each of these fundamental options, so you can refer to them from the top itself, right? Using the different tabs. Right? And then finally, we have the visualization part itself. So the graphics part where you can visualize either your 2D or a 3D geometry. Right? So this is a basic overview of COMSOL graphical user interface. So keeping time in mind, so I have already imported the basic geometry. So in COMSOL, we also have what we refer to as geometry part library, right? So we have different configurations of motors, rotors, rotor stators, and magnets, right? So you can readily import those parts into your user interface, right? So if I right click on the geometry part, so I can go to the part libraries. And so these part libraries are basically grouped based on the different physics, right? So I can go to the AC/DC module, and if I go to, for example, rotating machinery 2D, so there are different configurations for rotors and stators, right? So we have the embedded magnet internal rotor. So we have the V-shaped internal embedded magnet, and we also have the surface mounted magnet, right? So similarly for stators, so we have the slotted external stator in 2D. Similarly, we have it for 3D configurations as well, right? So suppose you don't have a ready-made CAD geometry, you can import initially from the part library of COMSOL itself. Right? So I have already imported such CAD geometry that is available within the part libraries. Right? So now we'll slowly set up this particular motor model, right? So we'll explore the various options. So yeah, so if we go to the component itself, and if I expand on the geometry, so I'm importing this particular rotor geometry, right? And all of these geometries are essentially parameterized within COMSOL, right? So what I mean is, if I go to the settings and if I expand on the input parameters, so the different aspects of your particular rotor, right? So it can be the number of poles, so the shaft diameter, rotor diameter, magnet height, width. So all of these aspects are already parameterized. You just need to change the expressions, right? And these expressions can be in the form of values or numbers, or it can also be in the form of parameters as well. Right? And for example, this parameter NP, which signifies the number of magnetic poles in the rotor, has been defined as a parameter, right? So I can go to parameters here, and here you can see this particular parameter, right? So these parameters has also been, initially imported, keeping the interest of time, right? So yeah. Right. So similarly, we have the stator as well that has been parameterized. So the number of slots, the back iron thickness, stator diameter, among others. So all of these have been parameterized. Right. Yeah. So once the CAD geometry is there, so the next part would be to assign the different materials to the different domains, right? So if I expand on the materials itself, so initially we have the air. So we are assigning this air material properties to the interface of the rotor and the stator, right? So what we refer to as the air gap between the rotor and stator. So then we have the soft iron, right, without losses that we have assigned to the various iron domains within the motor, stator and the rotor, right. And for the copper windings, we are assigning the copper material, right. So then we have the magnet material, which is the N54 sintered magnet. So we have assigned these 5 magnet domains, right. And then we have the high strength alloy steel for the motor housing and also for the shaft. So we have the high strength alloy steel that has been assigned. Right. So so you might be seeing that we only have a half sector geometry, right? So initially in one of the slides, I was referring to how you can implement the sector geometry, right, to reduce the computational load on your system. So this is a live example that we have, right? So we are only considering the half sector of your entire 360 model, right? So we are only considering the 180-degree model. Yeah. So since now we have the geometry and we also have assigned the different materials, now we need to move on to the boundary conditioning part, right? So for that we will have to add the physics interfaces, right? So I'll go to the physics tab on the top, and here you can see the add physics button, right? I'll click on it, and you can see that so all the interfaces have been categorized based on the physics, right? So AC/DC, acoustics, heat transfer, fluid flow, and so on. So we'll go to AC/DC, and within that, so we'll go to electromagnetics and mechanics, right? So under that, once again, we have several physics interfaces. So rotating machinery, magnetic, so which is what we had initially. So that has been improved upon by the time periodic interface, right? So we have the magnetic machinery, time periodic. So yeah, so I'll add this physics interface to our component. So I'll click on add to component. Yeah, so as this is a conference machine, so there's a bit low. Yeah, so now you can see the magnetic machinery time periodic interface has been added under the component 1. I'll close this. And within this, so we can add different kinds of boundary conditions, right? So if you right click on magnetic machinery, you can you get access to all the boundary conditions, right? Yeah. So if I click on the magnetic machinery time periodic, you get to see the corresponding settings, right? So in this, you get to define a set of inputs, right? So which are essentially the electromagnetic related parameters, right? So which is the time periodic electrical frequencies and the number of time frames you want to solve for, right? So within the time periodic, so then we have the dependent variable grouping, so motion type. So you can define different kinds of motions, right? So you need to define the number of poles of the magnet, right? So yeah, so since we have defined all the parameters for each of these, so I'll just basically go ahead and type in these parameters. Right? So once again, first of all, the out of plane thickness. So we have a parameter defined as L, right? Yeah, so this length is around 0.05 meters. Right? So similarly for the time periodic electrical frequency, so we have a parameter defined, so F underscore EL. For the number of time frames, so we have a parameter named N frames. Right? And finally, we have the number of poles. Right? So that is defined as NP. Right? So if you look at it, the value is 10. Right? So here you can see we have modeled 5 magnets within the simulation domain. Right? So 5 magnets, hence 10 poles. Right? Yeah. So once that is done, so yeah, so we have to add the rotational boundary features. Right? So I'll just click on add rotational boundary features. So that adds a couple of boundary conditions here automatically, right? So which is the rotational continuity pair, right? So between the rotating parts and the stationary parts, so we need to have continuity, right? So for that we have the rotational continuity pair that is highlighted in dark purple here. And if I click on rotational periodicity, you can see that the periodicity has been defined on this boundary, right? So it is periodic about this boundary. right? So that is done. So now we'll add a rotating domain feature, right? So if I right click on the magnetic machinery periodic, I have this rotating domain feature. So now, so since this is a part imported directly from the part library, COMSOL is intelligently detecting what is the rotational domains, right? So, so under the rotating domain, it has automatically selected all the domains, right? So the relevant domains. So yeah, so in this we have option to define how we want to basically define the time periodic rotation, right? So if it is a synchronous pole pair, full mechanical revolution, if it is a non-rotating or a user-defined feature, right? So if it is a linear machine, for example, a linear motor, right? So for that you either go with the user-defined or a non-rotating option, right? So in this case we'll go with the full mechanical rotation and rotation direction as well, right? So that can be specified. Yeah, so we'll go ahead with counterclockwise. So the rotating domains have been defined, right? So now we'll define the laminated core, right? So basically the constitutive model that we need to define. So rotating domain is done. Now I'll add the laminated core. Right? So now I'll have to so define or select the iron domains, right? So for that, it is asking me for the domain selection. I'll select all the relevant boundaries, right? So which is on the rotor, then the laminations, right? So yeah, so these are the two domains that we'll be solving for, and we need to define a certain magnetization model as well. So it can be coming from the BH curve for that particular material, or it can be from a relative permeability model as well, right? So for these BH curves can also be user defined as well, right? So if it is coming from any of your suppliers, so you can request the BH curve from the supplier itself and implement it as one of the interpolation functions. So within your material properties. Yeah, so the magnetic field normal, magnetic co-energy density is getting obtained from the material itself, right? So once that is done, so the next step would be to define the loss model, right? So the loss model can be Steinmetz, Bertotti, or you can define your own loss model as well, right? So these are some of the empirical formulations. So yeah, so we'll retain the Steinmetz model. So once that is done, the next step would be to define the magnet itself, right? So yeah, so we'll add a magnet boundary condition, so or a domain condition in this case, and we'll select all the magnet domains, right? So we have 5 magnet domains in this sector. Yeah, so once that is done, we need to specify the direction method, right? You can either specify the north and south boundaries, or you can specify by domains as well. So if you have different separate domains for the north and south boundaries, right? I'll go with the specify north and south boundaries. And the pattern type can be a circular pattern or a linear pattern, depending upon your configuration. So I'll go with the circular pattern. Right. So the pattern center, it is automatically taking it at 0, 0, right? So the X and Y coordinates. And then we need to define a certain magnetization model as well. Right? So this can be a remnant flux density itself that is being taken from the material properties, right? And yeah, so you can define the constitutive relation. So that can be from the material, or you can be user defined as well, right? So if you're interested in knowing the losses as well, so you can define on the loss model as well, right? In this case, it can be resistive heating due to it can be due to the eddy currents, for example, right? Yeah, so once that is done, so if I expand on the magnet, so it is asking me for to specify north and south boundaries, right? So what I can do is I can click on north and select the north boundaries, for example. So I can select these 3 boundaries, right? And I can click on south and select the south boundaries, right? Yeah. So now once that is done, so it automatically selects alternating north and south boundaries for the other magnets as well, right? So because we are defining it as repeating periodicity, right? Or in this case, it needs to be alternating periodicity, right? So yeah, so based on that, it automatically considers the alternating north and south polarity of the magnets, right? Yeah, so the magnet part is done. So the next step would be to define the electrical excitation, right, for the copper conductors here. So for that, once again, I'll right click on the magnetic machinery interface, and you can see the multi-phase winding feature, right? So there's a dedicated feature to basically define your electrical excitation. Right? Yeah. So once I add that, I need to define the domains as well, right? So where the copper coils are. So I'll select all these copper boundaries. Right. So now I need to define, the peak phase current, the initial electrical angle, the winding electrical frequencies, right, for these. So for that, once again, I have already created parameters in the parameters section. Right. So I'll just directly type in those parameters. So the parameter for the peak current is IPK. For the initial electrical angle is init underscore angle. Sorry, underscore angle. Right. And for the winding electrical frequency, it is F underscore EL. Right. And you can also define the winding layout configuration as well, right? So typically 3-phase is most common. So if you're working with any other winding configuration, you can define those under user defined configurations. Right. For now, I'll go with automatic 3-phase. Right. So once I select that, so I'll have to now define the number of poles and the number of slots and number of coils per slot as well. Right. So for now, the number of poles is getting directly obtained from one of the earlier boundary conditions. So there is no need to change that. For the number of slots, I have defined a parameter. So NS, right? And so we have 2 coils per slot, right? In each of these slots, we have 2 coils. So that is what we are defining it here. So once that is defined, you can click on add phases. Right. So once you click on that, COMSOL automatically defines 3 distinct phases, right? And you can also see the relevant the domains that have been selected, right, for the 3 electrical phases. And you can also see the phase offset angle, right? So for the phase 1, it is 0. For phase 2, it is -120 and -240 for phase 3, right? So you also have the option to change these as well, depending upon your configuration, right? And you can also see the reverse current direction as well, right? So for the automatic phase 1, so this is the configuration. And if you want to see the reverse current direction, you can see that as well, right? So where basically the current is getting reversed. Right? Yeah. So once that is done, so basically the electromagnetic part of your boundary conditioning is done, right, for this particular electrical motor. So since we are interested in plotting the efficiency maps, for example, so we need to include physics interface from the heat transfer in solids as well, right? Yeah. So for that, once again, you need to go to add physics, and so if you go to the heat transfer, so we have several interfaces, right? So heat transfer in solids and fluids, conjugate heat transfer, radiation, electromagnetic heating, and so on. Right. So once again, I can go to heat transfer in solids and click on add to components. Right. So similarly, we need to do boundary condition setup for the heat transfer in solids as well. Right. So yeah, so in the interest of time, so I already have a ready-made model setup. So that is a solid model. Right. I'll just basically go to that model, and we can look at how the boundary conditioning is done for the heat transfer in solids as well. I just open the solid model. So yeah, so basically we looked at the different boundary conditions from the electromagnetic perspective. So if you look at the heat transfer in solids as well, right? So we are solving the equations for heat transfer in solids for the entire domain, right? And yeah, once again, we have continuity that we need to define, right? So between the stators and the rotors. And yeah, so in COMSOL, we have several simplification features, right? So let us say you're trying to model thin layers between the laminated core and the housing, right? So for that, we have a dedicated thin layer features, right? So if you explicitly try to model these within your geometry, so these are very high aspect ratio components, right? And that can take a lot of time and so drastic increase in the number of elements that you need to include, right, to model these effects. So we have these thin layer features. So similarly for the winding insulation, so between the lamination and the winding, so you can model the insulation. So if there are any thin air gaps and you want to model that, you can model that as well. And we have defined a heat flux to model the water jacket in the motor house. So we have used this particular heat flux boundary condition, and where we have modeled a particular value for the heat transfer coefficient, right, for this active cooling method. So similarly, you can also explicitly model the cooling channels as well, right? If you want to optimize for the cooling channels or for the flow rates and so on, right? Yeah. So similarly, we have defined a heat flux for the air gap as well, right? So that you can see here. So because of the rotation, so that can lead to convective heat transfer between the stator and the rotor, right? And we need to implement those heat flux boundary conditions as well to accurately get the temperature distributions in these regions, right? So for that we have it. Yeah. So once again, a periodic condition to let you know that we have considered only the 180 degrees for this, right? Yeah. So once again, we have several of these simplification features when it comes to be it the heat transfer in solids or also the magnetic machinery time periodic interfaces. Right. Yeah. So the multiphysics coupling that we have is the electromagnetic heating. Right. So because of the different electromagnetic losses, so those will act as heat sources for the temperature rise. Right. So for that we have this electromagnetic heating multiphysics coupling that is essentially coupling the electromagnetic and the heat transfer physics interfaces. Right. So it does the job of transferring the variables from one physics interface to the other. Right? Yeah. So that is on that part. So since this is a finite element based tool, so we also need to create the mesh in some sort, right? So for that as well, so within console, so we have two approaches, right? So one is the physics controlled mesh. So it automatically considers the underlying physics, so which will be the contributors, right? And it creates an automatic mesh. But if you want to have a better control over your mesh, you can switch over to the user control mesh and create multiple refinements in multiple regions if you think that is needed for your particular model, right? Yeah. So this is on the meshing part. Yeah. So then comes the study type, right? So once again within studies, so if I go to the study tab on the top, and if I click on add study, right? So here you can see we have options to include multiple types of studies, right? So be it the basic stationary and time dependent study. You can also include various frequency domain studies as well, right? So frequency stationary, frequency transient, and so on. So for structural mechanics, so we have the eigenfrequency studies or frequency response studies and so on, right? So multiple options are available. So in this case, we are running a parametric sweep of the motor rotational speeds and also the peak currents, right? So we are running it for a range of speeds and currents. And once that is solved, so we get the results for those simulations, right? So if I click on the magnetic flux density, so you can see the distribution of magnetic flux, right? So yeah, so this is the magnetic flux density distribution solved as a stationary study. Right? So here you can see that the maximum value is around 1.83 Teslas. Right? So similarly, we have the temperature distribution as well, right? So which is around close to 400 Kelvin. Right? So this is a temperature distribution due to the various electromagnetic losses. Right? And so if you're interested in plotting the motor efficiency maps, so that can also be plotted. So to obtain the optimum working range for that particular motor, right? So that can also be done. So the electromagnetic losses for different rotational speeds and peak currents, right? So similarly for the temperature distribution as well. So we saw these plots in the slides earlier. So it is the same thing for different speeds and peak currents. Yeah, so this was basically on the demonstration aspect. Let me quickly switch back to the presentation. Yeah. So we just looked at the different aspects of electrical machine and in particular the electrical motor modeling, right? So one of the major aspects of our electric drivetrain is the power electronics component as well, right? So which can be in the form of inverters. It can be three-phase inverters as well, right? And these three-phase inverters are basically housed in a very compact kind of a volume, right? So that can lead to several electromagnetic and resulting thermal effects, right? So, and the main purpose of this slide is to demonstrate how you can couple different underlying physics, right? So if you are coupling the electromagnetics and electric circuits interface with solid mechanics, so the electromagnetic interface basically gives the different magnetorestriction and the Lorentz forces to the solid mechanics, which in turn computes the deformations due to those forces, right? So similarly, so the electromagnetic interfaces basically giving the various losses, right, to the heat transfer interface, which in turn computes the temperature distribution as a resultant, right? So similarly, if you're interested in doing any thermal management kind of simulations, right? So there you will have to include conjugate heat transfer kind of studies, right? So you can couple that with CFD interfaces. So if you're interested in doing any NVH kind of analysis, you can couple it with acoustics interfaces. So that leads to sound pressure distribution in the surrounding domain. And of course, you can optimize your entire system, keeping any of the objective function in mind. Right? So this is for the power electronics, but it can be for any other system as well. Right? So based on this particular slide, so we have another case study from Bosch, right? So Bosch is, as you might know, is one of the major tier 1 suppliers to OEMs, right? So automotive, defense, aerospace. So in this case, so this is a coupled electromagnetics and heat transfer analysis of a three-phase inverter, right? So typically three-phase inverters are placed between your electric motors and the battery packs, right? So in particular, so this is for a DC link capacitor, which is one of the crucial components inside the three-phase inverter, right? So they have performed coupled electromagnetics and thermal simulation, right? So to basically check if this particular layout is going to hold the maximum limits of temperatures, right? Here you can also see the measurement and also the COMSOL simulation results as well, right? So which is in good agreement. So this is one such case study from them. Yeah. So so last but not the least, we'll also look at the different aspects of battery design that you can implement using COMSOL multiphysics. Right? So when it comes to the battery models, so you can start off at very basic battery electrode level modeling, right? So where you consider the different heterogeneous models, right? So you can consider the porosity of your electrode. So yeah, so that is the level of detail that you can implement. And you can homogenize those properties and do your simulation at the system level as well, or at the battery pack level, right? So you homogenize at the cell level, and basically in the end you can consider 1D models, right? So between several cells in your battery pack to do electromagnetic or electrochemical simulations, but you can do the heat transfer analysis at the pack level, right? So that can be in 3D. So yeah, so these heterogeneous models, so they are very accurate, and you can do it for a wide range of parameters, right? But they are very expensive to compute. So you can homogenize the properties, and you can do it at the lump level as well. So those you can obtain the results very quickly, right? But it has a very limited range of validity, and so sometimes if you're looking exactly at the accuracy part, so it might not match your requirements, right? But at the system or the pack level, it is very accurate. Right? If we talk about the scales when it comes to battery design, like I was saying, you can model it at very electrode level, homogenize at cell level to perform any electrochemical simulations. And once again, you can homogenize it at the pack level as well. So if you are interested in any thermal management level simulations, right? Yeah. So we have what we refer to as proof of concept model, right? So typically in any simulation, so the validation is very important, right? So for that, if you go to the COMSOL website, so you can download this model, right? So this is a very typical configuration of an electric vehicle, right? So 8 rotor poles, 48 stator slots, different skewed configuration for the stators and the rotors, and V-shaped magnet configuration. So 240 kilowatts, 460 Newton meters. So all of these are typical, EV kind of configuration. So you can download this model from the COMSOL website and look at how this particular electromagnetic simulation has been set up for this motor, right? And you can also refer to this motor tutorial series as well, right? So that is available in the COMSOL website itself. Yeah. So with this, we have covered the entire range of electric drivetrain simulations that can be done within COMSOL. So based on this, so I request all the attendees to just let us know if you would be interested in getting in touch with so one of the POCs at COMSOL, so that we can discuss more in detail regarding your simulation requirements, right? Yeah, so poll question is launched and it should be visible on your screen. I request you to select the appropriate response. Okay, so probably meanwhile we can take up a few questions as well. Yeah, so there is one question. So how to model inverters along with the motors? Okay. So one thing is, so you can do the inverter control within MATLAB. So we also support co-simulation with MATLAB, right? So you can do the finite element modeling of your motor within COMSOL, and for when it comes to the control aspect of it, you can go to MATLAB, right? So that's how most of our customers do it as well, right? So there is another question: how to begin with deciding the specifications of electric motor for an EV? Yeah, so that, if you want to give me an overview, that typically depends on the kind of load that you are designing it for, right? And so there are several literatures also that are available. So for that case, you can also refer to this proof of concept model as well, that we were discussing in the earlier part, right? Yeah. So yeah, so there is another question. If someone wants to do the simulation for PMSM 6-phase, then what would be the changes in the boundary conditions? So, sir, yeah, so we were basically demonstrating on the multi-phase winding feature, right? So there, if you remember, you can change the number of windings that you can specify, right? Apart from the default automatic 3-phase, you can also specify any user-defined electrical phases as well. Right. In doing so, you can model 6-phase or any other configurations as well. So will we receive any certificates following the webinar? So that probably you'll receive an email, I believe. So probably Amal can add more on it. So what should be the file type that I have to export from SolidWorks to open on console? So yeah, so there are multiple options, sir. So we also support what we call as live link with SolidWorks or any other CAD software, right? Be it CATIA, Pro-E, and so on. So if you have that live link license, then you can directly install it on the same machine where you've installed console, and you can basically interface console with SolidWorks, right? So then you can import any of the SolidWorks file format itself. But in case that is not possible, you can go with the CAD import module, right? So when you have the CAD import module license, you can import any of these SolidWorks or CATIA or Pro-E or NX file formats within console, right? But in case you don't have the CAD import module as well, so you can export the CAD geometry as a parasolid from the SolidWorks, right? Parasolid, or it can be IGS. You can export it in such standard geometry formats, and you can import it within Solid console. Yeah, so there is another question. Yeah, so do you have any PMSM case study and NVH case study? Yeah, for that, I'll directly go to the console website itself. Okay, so if you, sorry, I'll just close this particular poll. Yeah, so now if you go to console.com, yeah, so and if you scroll down in the website, right, so we have different links for the various resources, right? So you can open the models and application files, or you can go to the papers and research, right? So where we have many of our esteemed users who have published different papers using console. You can also refer to the several of the case studies and user stories from many of our academic as well as commercial and government customers, right? So since you're asking for the models, I'll go to the models and application files. And here the models have been categorized based on the physics. Right? For example, here you can see the cable tutorial series, FSI example, structural mechanics, and so on. Right? And if I just search for motor here, so once again, we have models for different configurations, right? Induction motors, electric motor noise, right? So since you are interested in the NVH, so you can go to this particular motor, particular link. And so once you get a hold of the trial license, for example, or if you're already a user, so you can go to this download files tab and you can download this particular model. Right? And you can also download the relevant PPTs and also the PDF files as well. Right? So that has the detailed description on how this model has been set up, for example. So similarly, you can go to the papers and research as well. Right? So there are multiple papers that you can refer to on this. Right? So once again, if I search for motors itself, yeah, so there are multiple papers. For example, this from IIT Guwahati, so from Simtech. So we have similarly from Bosch, Volkswagen, ABB Corporate. So yeah, you can download these papers. Yeah, so another question. So do you have any case studies on synchronous reluctant motors? Yeah, so we do have case studies on these as well, sir. So so you can obtain these case studies, technical papers, and if available, models as well from the console website itself. Right? Yeah, so yeah, I think so. We have come to the end of the session, and as a concluding remark, I would like to say to all the attendees that using COMSOL, you can do diverse kind of simulations when it comes to electric motors and drivetrains. Right, so you can carry out very fundamental level simulations at a very component level, and you can also do it at a system level as well, right, by integrating, for example, MATLAB or Simulink. And one more thing is you can do such simulations ranging from electric motors or different configurations, right? So different working principles, and also for the power electronic components, and also for the battery packs as well, for different chemistries and for different scales, ranging from electrodes to the battery pack level as well, right? In conclusion, I would like to request all the attendees to explore more of your simulation requirements using COMSOL as the tool. Right? So, yeah, I think with this we have come to the end of this particular webinar. So, yeah, thanks everyone. Yeah, so there is another request for the super capacitors as well. Yeah, yes, ma'am. So there is. Yeah, so there are case studies available for this. I would request you to go to the COMSOL website itself. Or if you want to discuss in more detail, I would like to request you to get in touch with us by sending a mail to support@comsol.com. Right. So one of our representatives will get in touch with you, and we can have a detailed discussion on your particular problem statement. All right, yeah. Yeah, so thanks once again, everyone. So we hope this particular webinar was of help and revealed a lot of information when it comes to the simulation aspects. Yeah, so thanks everyone. Good evening and have a good day.
Very good.